lecture slash research talk. And I'm really happy to introduce Arthur Leroy, who is based here at the University of Manchester, working with us on mostly multi-output, multi-task Gaussian processes.
Thank you, Mauricio. Can you hear me well? Okay, no disturbance. Perfect. Cheers, Magnus. So, a bit misleading, the title, because for people who know a bit about Gaussian processes, I've stolen the multitask Gaussian process term to refer to something I'm doing myself, but people like 10 years before me have named things multitask Gaussian processes, even though it's completely different. So I will try to give you a taste of what we can do, not with only one Gaussian process, but with many more at the same time. And we'll see different strategies and the ones I personally developed in order to tackle some problems I will discuss. So let's start with an illustrative example. It's actually the example and the problem that kept me working for 3 years during my PhD. This problem comes from elite sports. It's actually swimmers that you see here, swimmers between 10 and 20 years, and what we are looking at, what we are measuring is their performance on the 100-meter freestyle, classic swimming pool. And what we are looking is each point corresponds to a performance that at a certain age the swimmer has accomplished. So, okay, we see that the performances are decreasing in time, meaning that the swimmers have improved over the time, which is kind of normal. And you see that in green, red, and blue, I've differentiated 3 different individuals in this graph. So I will talk throughout this presentation about individual tasks, outputs. All those things mean the same thing here. It means that we don't have only one source from which we observe data, one source of correlation, but we have many. And what we can see in the problem I had is those points here can be seen in general as time series, but those are really irregular. And for those of you who know the time series literature, you know that you can throw away 95% of the literature on the subject when you have irregular time series. You also see that you have only a few observations per individual, but in general you have like many individuals. In my case, I had a few thousand up to millions of different swimmers. So that's something we hope we can take advantage of. And in this case, what can we do with that? We have really irregular observation, not the same number of data points per individual, not the same location. What we like to do is work instead of time series, is work with curves and functions. So that's why GPs are going to be involved in all this in order to draw a comparison, those kind of stuff. So a little bit of recall. I know it's fresh, it's been this morning, but I'll try to quick recap of my point of view of this problem. The classic regression framework, inputs x, outputs y. We try to determine the function f that maps x into y. Instead of imposing a structure of f, we are just putting probabilities through a prior distribution on f, which is a GP, and I don't know what. Okay, you are connected to internet. Okay, that's GP in the 2 squares, but okay, no worries. So now you're familiar with GPs, you know that the covariance structure is critical, and in general people say, oh, we don't care about the mean structure, like the mean parameter, just don't care about that, it's not important. What I will try to convince you during this talk is, nah, you can do things with the mean process when using it properly. Even though I agree, covariance structure is really important, so you can use different kernels. During the lab session, you've used probably the squared exponential or exponentiated quadratic or LBF, whatever. And you can see examples of different kernels, so the periodic one in the middle and the linear one on the right side. So you can see that a linear regression in the Bayesian framework is just a particular example of Gaussian process regression. And so we've drawn 3 functions from those prior each time. Okay, we know about that now. It will be maybe complicated. Yeah. Remember that on the squares, it's just GPs or Gaussian distributions, and it will be easier to understand. So Carl and Rick talked about that a little bit. Yeah, I think it's not too bad for the remainder of the talk. It's just n. Basically, it's n. It's Gaussian. That's all right. For now, square is n. Maybe just reload the page.
I don't think it's going to work.
Are you connected to internet? That's weird because before it was working. So we have a bit of time to remember this property, the fact that we have the Gaussian property that is absolutely key here that helps you going like zoom on the observed point or de-zoom to the full process. And the properties, yeah, no worries. We'll deal with that. Telling you, oh yeah, that works.
Oh, it's the one that, sorry.
Oh, that works here and doesn't work here.
Yeah, sorry.
No worries at all. Yeah, so the fact that it remains Gaussian under marginalization and under conditioning. Brilliant. Yeah, technology, guys. Technology. You know, here in Manchester, we don't have internet. We do what we can. Give us found. And we don't have presentation anymore. Mauricio? I'll try myself. Exit. Full screen. All right. There.
That's weird.
Enough for full screen, maybe.
Yeah. The whole desktop. Can you do it like that without full screen?
Yeah, just do like that, maybe just a little bit larger if you can. It will do. Brilliant.
I'm sure.
Perfect. All good. Okay, you had time. And so now your favorite formula, prediction formula, condition over the observed values. You can predict what I've called FM for missing. It's exactly the same to say that an output is missing or it's the value you want to predict for GPs. So values of missing, condition over observed. You have your favorite formula, but from what I remember, I think Carl and Rick at least, he removed this term because in general that's 0. Okay, because if we assume that the mean is 0 everywhere, this term here disappears and this one as well. But you will see afterwards that it's important to keep them explicit in the formula. Okay, cool. Quickly, exactly as Carl said, we can draw samples to represent what it's prior. So if we assume a 0 mean and a simple RBF kernel, we'll have values like that. Then you know that the next step is to learn hyperparameters, optimal values. So you can see here we've trained on these data points the hyperparameters values. You can see then that the length scale and the variance of the GPs are adapted now. The length scale is slightly larger, but you don't go through the points yet. You've just trained your GP. You've not conditioned over the data point yet. And that's what you will do afterwards. So you condition over the first point. It imposes to go through it. And then, even though, I'm really sorry, I don't know if he's in the room. I will use this representation, not because it's better. I know the left one is better. But you will see that my graphs get really easily messy because there are things everywhere. And if I also put like moving curves everywhere, it's impossible to see what happens. So I will use a right-hand side like a way of representing things. And I assure you that those are just nice curves, but they are underneath. Okay, it's not some weird wiggles. You condition over additional points, and you see you constrain more and more, and now you're used to that. your nice GPs, and we have a really nice non-parametric and probabilistic way to reconstruct functional signals from data points. And we know now that the only problem of this is the cubic complexity, the number of observations. Not the only problem, but one of the main problems. Okay, but how is it important in the thing that we were the most interested in, which is long-term prediction? Because what I didn't tell you about is with my swimmers, I was working with the French Swimming Federation, and what they were interested about was, are we able to predict the performances of young swimmers in a long time to help us with talent detection problems? So are we able to do that? And if we fit a GP on each swimmer individually, that's what we will have. So we've observed the black dots. The red dots are the truths that we have hidden, so those are testing points. And you can see that if you stop around like a little bit before 5, your prediction will dive to 0, the prior value, quite quickly, and the uncertainty will increase a lot. And of course, it does what we like, which is if you add new points, the prediction will adapt. Just like that, and the uncertainty will decrease accordingly. But in the first place, when we have only a few data points and we seek long-term predictions, it's not really accurate. It's not really useful in practice. So can we do something about that, considering that, as I told you, we have sparse observation per individual, but we have many, many individuals? Can we take advantage of that to come up with new solutions? And that's why people have been investigating that for a long time now, I think 20 years at least, and came up with approaches that are quite natural when you like GPs. So multi-output GPs is all about leveraging correlation existing across multiple tasks and modeling this all together in order, we hope, to get better prediction or better modeling in different situations. And to do that, because people are really interested in general in designing a kernel function, we adapted multi-output kernels. There are many, many ways to build multi-output kernels. I'm just putting here a really simple example and simple way to do so, but we can do more sophisticated thing for sure. Instead of computing the correlation only between two inputs, T and T prime, we also add I and J, which are indexed for the individuals or the task we are looking at. And so we'll have the covariance between those objects that can be, in the case of separable kernels, be written as the product between a kernel on the outputs and a kernel on the inputs. Okay, so the object on the right side is exactly as before. What we have added is an explicit kernel to take into account the correlation between tasks. And in terms of writing, this is for the functional aspect. And when you have observation, it's exactly the same as the vectors of observation that you have for all your individuals. You stack them all together to create a big vector, and the covariance matrix of this object will be written like that with the Kronecker symbol as the covariance matrix of the output times the inputs. Okay, so as I told you, many ways to do so, and to be fair, I'm not exactly an expert of this way of doing things. If you have questions about that, there is a real expert who is Mauricio. He's done a lot of work about that. One of the problems here is it's in general really complicated to estimate this matrix KO, because you cannot really except on really special case. You have to optimize this, find values for it from data, and it's in general really unstable and really complicated to do so. And as you can see, the cubic cost that was already huge is now crazily big, with m cubed times n cubed, where m is the number of tasks you have at hand. Okay, what does it look like visually? Once again, an example of what happens with the Kronecker product. If you have your matrix KO here, let's say that we have a diagonal structure where only the terms in black, the diagonal in black is non-null, and some structure for the input, sorry, you would have this structure for the total kernel. Okay, you can see that you are combining kind of both structure. Of course, in the general case, the terms outside the diagonal are also have values that they are not zero, so it's way more complicated. And inverting this object, you can imagine, that's why it's really expensive, okay, because you will have this cubic cost. It's just to give an idea. But good thing is you're modeling every output-input couple and the correlation between all of them. And what you can achieve using those, once again, thanks to Mauricio, in one of the articles you can see that. So those are sensors there where it's sensors from meteorological station, if I remember well. And you have one component of your, so one output is on the left side, one other output is on the right side. And the top line, we used independent GPs to model them. So when you have data, that's all right, but you can see here you don't have data anymore, and so your uncertainty increases a lot if I treat that independently from the other signal. Same thing here. But if you model them with a multi-output approach, so you would, in this area here, you have data for the first signal, but you're lacking data for this signal. So you will use those data points to inform you, to help you predicting this area, and conversely for this area that is unobserved for the first signal, but that is present for the second one. Well, it's kind of interesting. You can take advantage of different parts of the input space that are observed depending on the signal we're looking at. Okay, cool. If you want to learn more about that, because I told you it's been an active area of research for like a few years now. You have the talk of Mauricio at the GP Summer School 6 years in the past, and a few recent ones like a review, also really interesting, and also another interesting review of all the methods and the way to put a framework that is general enough to classify them in 2020. Cool. But as I told you before, that's not the approach I developed to tackle my swimmer problem. To be fair, for 3 years, I haven't even been aware that it existed, what was done before. So I had this idea in mind. Okay, what looks more like a swimmer than another swimmer? Those guys are really similar in a sense, that they are doing pretty much the same thing, and the trend that they are following is quite similar. They are improving between 10 and 20 years. The only difference is they are not improving at the same speed, and they have variations that are quite personal, I would say. So why not imposing a new model, which as before, our observation for an individual I, for task I, is a GPF plus noise, but now we add this process here that I will call a mean process, mu0, that you will see afterwards is common to every individual or every task. And for the other objects, I just use classical GP. So here we have a mean process that is common to everybody, and an individual specific process, Fi, which is just classical GP as you've been using during the labs, and a Gaussian noise. And I just assume that the individual processes are independent from one to another. And from this, just from those hypotheses, it follows that conditionally to the mu0, which of course is a latent process, it's unobserved, that's just a quantity we made up for the purpose of what you'll see afterwards. It's still Gaussian. It's still Gaussian, and more importantly, is Gaussian and centered on mu0. Okay, so for all individuals are conditionally independent, condition over mu0. They have a specific correlation structure to their own variations, and they have a common mean. Cool. We have a unified framework which is fully GP, that's cool, and it models what we are trying to incorporate as an information. Cool thing, as I told you, is it really naturally handles irregular grids of information. You don't really care where your observed data points because you are working with functions. And what we need to do now with this model is, as before, we need to learn hyperparameters, classic. But now we also have mu0, which is a latent quantity, so you have to estimate that from data. And what we'll do is not just giving a single point estimate, but we'll compute the full, what I call hyper-posterior distribution. It's just a posterior, but because it's on an object that is not of direct interest, I call it hyper-posterior. The problem is we have a likelihood that depends on mu0 and the individual are not independent so like the mu0 depends on the hyperparameters and conversely. So a little bit of notation just for you to follow the next slides. We are each y1 to ym are vectors of observation from the m different tasks, and I stack all this into y, and I stack all the time points, because you will need to look at the mean process everywhere we've observed something. So I pull all the timestamps into one vector t. And so kt theta 0, which is the covariance structure on the mean process, is evaluated on t, gray here, and all the individual covariance matrices are evaluated on ti, which is specific to the ith task. And we need to learn omega, the big set of hyperparameters, and as before, we just sum the covariance structure with the noise. Okay. You know about the last thing. If we are able to do inference on the finite set of observation, we have everything we need to extend it to the full GP. To tackle this problem, something really classic we can do is deriving an EM algorithm. And what is cool with that is the posterior distribution of mu0. So when we condition over the data, we have a Gaussian likelihood and a Gaussian prior. So we all know that it remains Gaussian, so that's really convenient. We have an explicit closed form formula to compute the mean and the covariance parameter. I didn't write the full expression of this, but that's really classical for people doing Bayesian inference. Nothing fancy here. Okay, and when we have that, we are able to derive the marginal likelihood that we want to optimize in closed form. So we have something that is kind of expected. So for each task, we have a Gaussian likelihood to maximize here. We also have a Gaussian likelihood that is specific to the mean process, okay? And remember that those are not evaluated on the same times, but with a few mathematical tricks, we can work this out. And you can observe that the new thing compared, when you compare to classical optimization with GPs, is those trace terms. Intuitively, those trace terms, they tell you that it's kind of a natural regularizer that comes from the equation. It tells you that your posterior covariance shouldn't be too far away from its prior. Yeah, basically. Okay, that was the easy part. So we just came up with an algorithm to learn every quantities we had in our model. That's cool. So now we have a mean process, we have a distribution for our mean process, and let's assume that we observed a new individual, but just with a few points. Like we have a new kid, and he has done or she has done just 2 or 3 competitions, so a few data points, but we want to predict in the future. So we have exactly the same assumption as before, because that's just the modeling assumption. It's also, its specific trajectory is centered around mu0 and with its specific covariance structure. And we want, as normal in GP, to derive an analytical predictive distribution at its new input, at any input that we're interested in. And we want to share information through the different tasks or different individuals. And those information, they are stored into the mean process. But now we don't have a mechanism to share this information with the new guy or new girl. And the problem is, I told you, we are conditioned over mu0, and you don't know how to incorporate that. And the target distribution, It's easy now because I will give you the answer in one slide, but it really took me 9 months to know just which quantity we wanted to compute. That's definitely not straightforward. And we are working with a new grid observation, but we don't really care about that, just math details. The thing is, we can sort this all out by defining what I call a multitask prior distribution. Prior distribution you will see, because the strategy is the same as before. We will create a big vector with the time points we've observed and the ones we want to predict on, and multitask because it incorporates information from everybody. So we condition on training data, and then we integrate over the mean process, as we do quite often in Bayesian statistics when we want to get rid of a quantity that we've not observed. And the magic of this comes from here. So you see the vector of observation for our new individual that is denoted by star, condition over all the data from everybody. It's written like this. This is just a classical probability, the composition of the integral. And I told you before that conditionally over the mean process, all individuals, all tasks are independent. They are conditionally independent. That means that this conditioning here on y, it disappears. Intuitively, it tells you that the mean process, it stores all the information that is important to share with others. Like everything is in mu0. So you can just remove this y here, and once you do that, you have this quantity that is just the modeling, like the conditional likelihood coming from the model assumptions, like y star condition over the mean process, so that's a Gaussian centered on mu0. And this quantity, this little guy here, we've learned that during training. That's the hyperposterior distribution over mu0 condition over y. So we have a Gaussian here, we have a Gaussian here, and if you followed this morning's talk, the result remains Gaussian. And intuitively, what does it tell you? It tells you that this new task that you partially observed, it's centered over the mean that you've learned during training for your mean process. So from data, you've aggregated data from everybody and you've created a mean process, and that's what you recover here. And the covariance structure, it will be the sum of the individual covariance specific to the star task plus the covariance that you've learned for your mean process. Okay, just watching time. All good. And then once you have that, you can just go through the traditional way of doing Gaussian process prediction now. You know, you cut in two parts, the parts you've observed in gray, the parts, the inputs you want to predict in purple. You create your little, sub-matrices here, and you can just condition over the observation, and you will end up with the classical GP prediction like this, with the form that you, like the structure you now know. But as I told you before, what we forgot about this morning was those two really key parts where it was 0 before. And now, instead of 0, we have a mean process that we have trained on data, meaning that when we don't have data anymore for the new guy or girl, we have already something that is given to you by the others. And the covariance adapts as before. You can find all this in the corresponding article if you're interested. Okay, it was cool. We've seen a bit of math. What we are interested in, how does it look like for real? I've used exactly the same data as before, the few data points as before when I was trying to do forecasting. And you can see that instead of diving directly to 0 as before, we are not doing that. We have this dashed line here. The dashed line corresponds to the mean of mu0, the latent mean process. And even though we don't have data points anymore after 5 years for this specific task or specific individual, we will not dive to 0. We will stick to the mean process in the future. And it will give you something really important. So if you have data points in this area of the input space from other persons, you are able to share it with this new individual or this new task to give you long-term predictions that are way more accurate and uncertainty that is largely decreased as well. And as before, the classic mechanism of the GP still apply. If you observe new points, you will still adapt your prediction and decrease the information even more. So what it creates, of course, if you've not observed, if you don't have any data for your new individual star and for any other either, of course your prediction will be also bad and will dive to 0. And if you already have data at the beginning between 0 and 5, the prediction is basically the same. But it creates an intermediate regime in the sense where you don't have data for this individual in particular, but you have data for others, so you will use them instead as a, I don't know, a proxy to what you really try to predict. Cool. But if you followed me here, you would tell, oh yeah, but compared to the previous approaches, like multi-output, you were modeling explicitly every correlation between each task and each data point. That's way more restrictive. You assume that we have only one main process going through all your tasks or data. That's completely unrealistic in real life. And I totally agree, even for my swimmers, like you cannot compare Olympic champion with you or me going for a swim on Sundays. It doesn't have any sense. That's why you can move a step forward and say, okay, maybe there are subgroups in my data. I can create clusters of tasks that are like close one to another, like that are resembling in some sense. And that's not too hard to do so in the model. This is the model we had from now, and if we just assume that we have Zi, which are clustering variables drawn from a multinomial distribution, and people who are used to play with Gaussian mixture models will see where I go with that. I will just extend the approach of Gaussian mixture model from vectors to functions with a mixture of GPs. What it will change is we now need to condition on these variables. It tells you that Zik equal 1 tells you that the individual I belongs to the cluster K. Okay? And instead of having only one mean process mu0, we now have K different mean processes, each one being associated with one cluster. And, oh, sorry, I forgot to tell that now we need to condition over the mean process and the, sorry, the parameter, so which is typically the weight of each cluster. And conditionally to those two quantities, each individual is independent from all the others, and we don't have a GP anymore, but a mixture of GP. So, yeah, just a linear, like just a sum of GPs with adequate weights and weights that sum to 1. Okay, cool. So, problem. We had a nice EM algorithm before, but now we cannot, we can't use that anymore because we have posterior dependencies between mu and Z. The prior distributions are independent, but when you condition on data, it becomes dependent. So we cannot use that directly anymore. But once again, Carl and Rick talked a little bit about that this morning. We can still use variational inference. And how will we use that to keep closed form approximation? So I've just put the formula that you now know. The true likelihood, marginal likelihood, can be decomposed into lower bound plus a KL divergence between the true probability here and Q, which is the approximation. And which approximation are we using here? We will use something that is the minimal approximation, something really light, to be fair. We don't have to impose any structure on Q. What we just say is the problem we had is the posterior dependency between mu and Z. So let's just assume that it doesn't exist. Let's just assume that the posterior distribution of those two objects, they can factorize. They are independent. Really like a really light assumption. When you have that, you are, of course, able to derive the lower bound, and you can maximize it to optimize your hyperparameters. But what you will win for free is a natural factorization over the clusters in the individuals, just like that. It will give you that the distribution over all clusters is a product on the clusters of Gaussian distributions. And those posteriors here have exactly the same form as before, what we had with the previous approach with one cluster. And same thing, same thing with the multinomial. We had a prior multinomial, and we also have a posterior multinomial. And here we also have a factorization, but not on clusters, but on tasks. For all tasks, you have this guy here. As before, we are able to derive and step, so as I told you, the lower bound that you can optimize for, to find hyperparameter optimal values. I've just highlighted in colors the fact that you have specific hyperparameters for the clusters, specific hyperparameters for each individuals or tasks, and those three parts, you can optimize them separately. So those are, but those can be done in parallel. That's quite quick. So it offers you 4 sub-models where you can consider, you can say share additional information. That's why I generally talk about these models as a double multitask, in the sense that it's multitask because you share information through the mean process, but you can also share information through the covariance when you assume that all the tasks share the same hyperparameters. You can do that. And in this case, if you have the same hyperparameters for all mean processes and all individuals, you will just have 2 sets of hyperparameters to optimize by optimizing just the sum that is here and the sum that is here. And if you want to be more specific, if you think that some mean processes have a really different trend compared to the others, you can make those hyperparameters specific to each cluster. In this case, you will have k+1 hyperparameters. You can do the same with the tasks, and you can do both at the same time. In this case, you will be the more flexible. In this case, you will be the more parsimonious. It will change a few things in terms of training, of course. The last one can be a bit more unstable because you have more hyperparameters to train, and this one is really robust. But overall, it's not that different in terms of learning. In particular, in terms of training time, it's quite similar. Okay, cool. As before, we have finished with the training. We just have to come up with a prediction formula, and we use the same strategy. We derive for each cluster, we derive the multitask posterior as we did before. So condition over the fact that this individual belongs to this cluster, I derive a Gaussian prediction that is specific to this cluster, but I can go a step forward again. And integrating over the variables z star k here, I can make them disappear, and it will create this nice overall formula for, like a unique overall formula for this new individual, which is a mixture of Gaussian predictions, where tau star k here is a probability of this individual to belong to cluster K. So you have a weighted average, weighted by the probability to belong to one cluster of a prediction that is specific to the cluster you're looking at. That's a long sentence that, once again, is way clearer with a graph. On the left side, so you have the background, the points for like each color corresponds to one individual, one task. And you can see on the raw data that you clearly have a structure where you have 3 different groups that generated the data. And if you use a previous approach with only one mean process, it will give you something in between, which you can see that the prediction is not that bad. Like, you recover the uncertainty correctly. You still are in the range of uncertainty, but yeah, it's a little bit, it's not really satisfying to see this. And if you use the clustering approach, so you will simultaneously learn the hyperparameters and the clustering structure, so you predict and cluster your task at the same time. And it identifies that the black dots belong to the red cluster and gives you a prediction that adapts to this trend that is specific to this cluster and gives you a way better prediction and uncertainty that is largely diminished. It kind of discards all information that is superfluous, yeah?
My question would be, do you define the number of clusters beforehand?
Yes, yeah, that's an entry of the algorithm. We have a formula to find automatically the optimal number of clusters, even though in practice, I think that's a terrible idea to do so. Like the number of clusters is just something you want to see as a practitioner. If you have time, let's look at 10 clusters. If you don't have time, just look at 2 clusters. You will have big trends quickly. And generally what happens is the two original clusters will divide into sub-clusters where you will see more accurate trends and all. But yeah, for the sake of publishing a paper, you derive a big criterion just with a formula to optimize if you want to. And it works quite well, to be fair, but I don't like using it in practice. All good? Any other questions?
I have a bunch. One question is, are the swimmers getting worse over time, some of them? Like, why is it periodic?
Sorry, second.
Why is that function going up? Like, is this the time that it takes for a swimmer to...
It's not at all about swimmers. Sorry. It's an illustration on synthetic data.
I see.
Yeah, no, sorry. I will show you the results for swimmers in the end.
And another question is, how would this method compare to just doing something pedestrian, like pre-processing your data to make it have zero meaning?
Oh yeah, just it's actually a good idea to compute the empirical mean of your data and putting it as a prior of your GP.
Right.
Yeah, that's what people do for simple GPs, of course. That's the comparison we have, I think, in 2 slides or something like that. But it's like a way better. What you will have, instead of diving to 0, basically, you will dive to the average of your data.
Right, but
with classical GPs.
That's assuming that it's constant. What if you do some...
Yeah, something like...
You're parameterizing the mean as a GP, right?
Yeah, we can do with splines, or you can... Yeah, people have been doing that. You typically using splines to model the mean process. It's Shi and Wang in 2008. They did that. It's not that bad. It works. It works not as good as that, but we've compared with them on the paper, you can see. And there are a few problems, in particular the fact that they don't account for uncertainty, because it's splines, not GPs. So that's why it's cool to have a fully GP model, something consistent. But yeah, people have thought about that too. That's true. Yeah, cool. Any other questions? All good. For those who are curious, of course, that was easy, this one. Our individual was really clearly in the red cluster, but what happens, and you can see that the probability to be in the red cluster was 1 here. So the mixture of GP's prediction is just one cluster-specific prediction here. But what is the cluster-specific prediction for the other clusters? Of course, those are associated with a probability 0, but if these black points were identified, so misidentified to be in the blue cluster, so you will see that you would dive to the mean process here in blue, and so it will be quite bad. And the same if you identified it to be in the green cluster, it will also follow the wrong trend. It can seem like it's a problem because if you identify the wrong cluster, you have something that is really, really bad. But once again, remember that those are associated with probability 0. And if the problem were trickier with clusters that are not well separated, you would have probabilities that are far from 0 and 1. And you will see in another example that the prediction would lie in between and still give accurate predictions. That's why you don't need to have like 20 clusters. Even if you have 3 clusters, you can still have predictions that are in between those because of those weights. Yeah, we compared with the things I presented you before, linear model of correlation, which is an old thing, but always interesting, and multi-output, as I told you about, multi-output spectral mixture, something quite recent. And you can see that, as expected, because the cubic term, like the cubic term for the task, you have something really crazy, and I stopped just with like 50 tasks and 30 data points, and it was already exploding. And so with the first approach compared to simple GP, we can, we have almost an order of magnitude less in terms of error. And if we are in the case of a group structured data set, we all, again, decrease from an order of magnitude in terms of error. So it was really, to be fair, it was surprisingly surprisingly good in terms of result. Didn't expect that at all. And in particular, in terms of clustering, because the method, even though we used cluster to help the prediction in a sense, we didn't build it at all to cluster curves. But compared to state-of-the-art curve clustering methods, A or I is an adjusted run index. The closer you are to 1, the better you cluster tasks. We were really close to 1, really good, and beating all those methods all the time. So we are really happy about how it recovered curve clusters and the predictions. Okay, cool. I talked to you about swimmers at the beginning. So how did it go with that? Quite well, to be fair. You can see here, and you can see why I didn't use, Carl's methods of putting many samples of a posterior GP, because here it would be just completely impossible to see anything. We have identified 5 typical clusters, so 5 typical trends of evolution of the swimmers. Typically they are in blue, ones that are good and remains good all the time. Typically they are really easily detected by clubs and sports federation. There are people who are always, not that good. And there are people in between. Those are the more interesting ones. And there is these purple clusters that is really interesting, and typically those are kids with late, late growth. Like they are, a little bit shorter and a little bit skinnier at first, and then they develop physically later than the others. And so in general, around the age of 14 or 15, they start to improve a lot quicker than the ones that were always better. And they generally get back and be really competitive when becoming an adult. We estimate that only 10% of the people, the best swimmers at 12 years, are still among the best swimmers at 20 years. So those type of methods are really useful. And when I discussed with actually the trainers for the French Olympic athletes, they were trying to detect, swimmers. I gave them names of people in the blue clusters, so the best ones. They knew all of them. And I gave them name of the ones in the purple clusters, just to see what fraction of the late ones they knew. And this fraction was 0. They didn't know any of those because they were focused and they thought, it's at young age that you can discover talents, but actually there are people improving at all time. So we were quite happy about that. But to be fair, I moved from application in like sports application to really different things. And currently we are working mainly on prediction of time series in genomics, predicting DNA time series. This application was the weight of children between 0 and 6 years. This is in months. And how the weight of children evolves. And what I told you about just before, even though we are 3 clusters, because this individual we have identified here before 2 years, that it belongs to in between the blue and red clusters. You can see that the prediction in the future are also in between, because we have a probability 0.4 that it's in the blue cluster and 0.6 that it's in the reds. There is a package, and yeah, curiosity, I'm an R user, not a Python user, but we were lacking a package in R because it was impossible to do GPs basically in R before. So I hope I try to code all this from scratch. As with classical GPs, you can extend to multi-dimensional inputs, quite easily. That's just natural to do so. Of course, I represented here an example in 2 dimensions with 1 input and 1 over covariate. And you can extend that to many more inputs, of course, but for the sake of representation here, you can see that the values of the output here, as you already have information, because the color here already corresponds to something that is close to what we will observe in the future. That's the equivalent of the, the curve that adapts to the new data. It's a bit hard to wrap your mind around that, but Okay, really quickly, an extension of that, as I told you, switched to prediction of DNA measures. So now the problem we had with Mauricio when we started the project was we don't just have time series associated with individuals, different individuals. We have time series that are associated to individuals, okay, but also to genes. So each individual has multiple genes, okay? So we have what I call 2 sources of correlations. Not only, and we could also think that each individual belongs to, I don't know, to a hospital and to a country or whatever. So we have additional sources of correlation. And what we realized is that you can extend the previous model by adding a new term that accounts for this new source of correlation. So now we have still a mean process that gives you the mean trend, but you have a perturbation that is specific to the individual you're looking at, and you have another perturbation that is specific to the gene of this individual you're looking at. And so it will give you 2 specificities. For those that are used to looking at mixed models, it really looks like mixed models with fixed effect and random effects, but in the world of function. It's not exactly equivalent, mathematically speaking, but in terms of intuition, it kind of looks similar. Don't go into details too much, but mathematically speaking, that's really complicated to find a way to train this, or I thought it was, to compute hyperposterior and all. But the key idea, which is quite odd at first glance, but is to compute not one, but multiple hyperposterior distribution for mu0. Each being conditioned over specific subsamples of the data. Typically, you will fix one source of correlation and averaging over the other. And you will create many specific mean processes, because the one that averages over all individuals, all the genes, is just a big mess. It averages everything. It's pointless. You can compute it. It's just pointless in practice. And once you do that, you can do something that is useful in practice. So what I display here is for 2 different genes. I have time series so that I observed at 3, 9, 48, and 36 months, I don't remember. And each color point corresponds to 1 individual. So I have time series for plenty of individuals, and here on the left side for 1 gene, and on the right side for another gene. And you can see that this specific mean process is representing the trend, the evolution of this gene in particular across all individuals. And the same for another gene here. Okay, and how can it be used in prediction? And you can see it's okay. If now you have, for the same gene, so you have the same mean process, the dashed line that we had before, the slide before. So the purple line turned into the dashed line here. Okay, complicated to follow this one, I agree. But so you have 3 points that you have observed. You're trying to predict the red dot here. And you can see that for two different individuals, this is an individual on the left, this is another individual on the right, you will still able to adapt both to the gene that you're looking at and the individual in particular. Okay? So you have an adaptive prediction depending on the context that is really useful. That's what I've called multi-mill GPs because I don't know how to name things anymore, so I need to come up with something. Not just results. That's what we expected to observe, and we are able to. The errors we are making in predicting points at 6 years are nicely recovered by this pink area, which is a 95% credible interval once more. So we correctly quantify uncertainty. And that's where I stop with the answer to a question that will probably come. We scale linearly in the number of tasks, and that's why it's so great. And thank you very much. Any more questions? Feel free. Yeah.
So you mentioned that previously when people talk about multi-class GPs, you're sharing information through covariance.
Yeah.
Why might you choose to do this rather than that? How do you, if you're coming to an application, how do you
Decide
decide?
between the two?
Yeah.
A thing that I didn't mention actually is in the version with the mean, we are basically assuming nothing at all on the covariance structure. And conversely, on the multi-output approach, they don't assume anything on the mean structure. So people who are keen to do so can combine both. I've not tried yet because that's a bit heavy, but you can. And I would say it depends. Like if you, in the like in the case of swimmers, it makes sense to have a common trend, you know, because that's individuals that behave quite the same. It makes perfect sense to use this approach. It's way more efficient, way more stable. Like the result, the training on this is really robust. You will have hyperparameters values that really rarely fall into like local minima or whatever, whereas with multi-output GPs, that's really a pain to optimize, and it's really long. This being said, if you have something with really, you know, I don't know, particular like correlation where you need to explicitly, where you have an interest to define explicitly all like input-output correlation, you would need probably to use multi-output GPs because that's more precise. You know, you're somehow reducing information by using only a mean trend or even clusters with mean trends. But it's much more parsimonious. So your data is compressed in a sense.
For the clustering, when you cluster individuals into the groups, do you look solely at the quantity of interest? So in this case, into the performance of the swimmer, or do you take external factors?
No, just the data you're seeing on the screen. Of course, you can incorporate more data. I've just showed examples with time series because that's really easy to visualize. But as I told you, the multi-dimensional inputs version is possible. And in this case, you would use everything you have at hand. We are currently, I have a few projects currently, no slide, extension to categorical inputs. So when you don't have, outputs that live in R, but what are just categories. Sparse approximations, that's crazily difficult, but I've finished the calculus, I think. That's just the extension of what Carl presented this morning, but in this context, there are many more technical difficulties and a few different things, but that's quite recent. Any people wanting to work on that, you're really welcome to send an email if you want. And I don't remember. Yeah, basically that's it.
Is the clustering done beforehand, or it's
At the same time,
at the same time?
simultaneously, yeah.
So the GP result affects the clustering as well?
Yes. How it works is, you know, that's an EM algorithm or VEM algorithm. So at the E step, you compute the posterior distribution of the mean processes, but also of the clustering variables. If you remember, I can just, it will be clearer. to get back to that. Right here. All the magic is here. Okay, so during the E step, you compute basically the shape of the mean processes, and you compute this little guy here is a probability to belong to each cluster for one individual. So you update all this, and this is a closed form formula. Once again, people used to Gaussian mixture. It really looks like the same thing as with vectors, but here we have functions. But that's just an extension. Most of it is an extension in the world of functions of things we do quite naturally in the world of vectors. Yes, that's it. Everything else? Yeah, we're all a bit tired now. I understand, me too.